So we're going to continue talking about functions of several variables, and we were talking about the chain rule, but now let's suppose w is still a function of two variables, but now x and y are functions of two variables, s and t. Well then, the partial derivative of w is really a function of s and t, so the partial derivative of w with respect to s would be the partial of w with respect to x times the partial of x with respect to s plus the partial of w with respect to y times the partial of y with respect to s. And then you also have a similar formula, but then instead of s you have t. So the partial derivative of x with respect to t, the partial derivative of w with respect to y, the partial of y with respect to t. So let's look at an example here. Find the partial of w with respect to s and the partial of w with respect to t for the function w is x squared y squared, x is s squared plus t squared, and y equals s. So we're going to use our formulas there. I take the partial of w with respect to x, partial of w with respect to y, and then multiply each one, partial of x with respect to s, the partial of y with respect to s. So here you get 2xy squared. The partial of x with respect to s would be 2s. Partial with respect to y would be 2x squared y, and then 1. 2x, so you'll get overall, maybe I'll simplify this a little bit, we'll get 4xy squared s plus 2x squared y. Now usually you'll want this just in terms of s and t, so just plug in x is s squared plus t squared, y is s squared, so this will be s cubed. So there's my partial of w with respect to s. You could also find the partial of w with respect to t in a similar way. The partial of w with respect to y times the partial of y with respect to t. So here, these first two pieces are the same as they were before, so I can just copy those down from earlier. It was 2xy squared, it was 2x squared y, and then the derivative of x with respect to t would be 2t, and y is just s, so the derivative with respect to t is 0. So I'm getting 4xy squared t. And again, you can plug in place of x and y so that it's just in terms of s and t. And there's my partial derivative of w with respect to t. Now, we also talked about, we're going to move on to our next topic, the gradient of f. So remember that it's the partial derivative with respect to x plus the partial, so if f is just a function of two variables, right, then you're only going to have two components here, an I and a j. So remember that this is a vector. You can tell that because it has an I and a j over here. It's a vector. So let's look at an example. Let's suppose f of xy equals x ln y plus x squared y squared. So you need to find your two partial derivatives, fx. Take the derivative with respect to x, you'll get ln y plus 2xy squared. Fy would be x over y plus 2x squared y. So then your gradient of f would be this first bit, ln y plus 2xy squared I plus x over y plus 2x squared y j. And you can find the gradient also for a function of 3 variables as well. So now we're going to look at a couple examples involving tangent planes and normal lines. And these ideas really build off of our gradient idea. So we're going to look at a couple examples here. So now let's find an equation of the tangent plane to the following surface. So z squared minus 2x squared minus 2y squared equals 12. So the first thing you want to do, I didn't finish writing the question, at the point 1, negative 1, 4. So the first thing you're going to do is take the equation of your surface, and you want to get 0 on one side. So I'm just going to move the 12 over. Z squared minus 2x squared minus 2y squared minus 12 is 0. So here I'm looking at a function of 3 variables. So I'm going to have f being z squared minus 2x squared minus 2y squared minus 12. And then you're going to find your partial derivatives here. Fx will be minus 4x. Fy would be minus 4y. And Fz would be 2z. And then you're going to plug in your point into these partial derivatives. So my point was 1, negative 1, 4. So you would get negative 4 for fx. Fy, you're going to get a positive 4. And fz at our point would be 8. And so these make up our direction numbers for our plane. So you're going to take that and then your point and write the equation down. So I have negative 4, 4, 8, and then my point 1, negative 1, 4. I have everything I need to write the equation of a plane now. It's going to be negative 4 x minus 1 plus 4 y plus 1 plus 8 z minus 4 equals 0. And you could simplify this if you want, or you can leave it like that. All right, and now let's talk about how to find the equation of a normal line. So let's look at the following example. Find a set of symmetric equations for the normal line to the surface x, y, z equals 12 at the point 2, negative 2, negative 3. So remember, if you're writing a point, the equation of a line, you need a point and you need a direction vector. So you're going to start by, again, getting 0 in your equation. So you're going to, on one side, subtract 12. So here my function of 3 variables is going to be x, y, z minus 12. And then you're going to find the gradient of this vector, the gradient of this function. Take the derivative with respect to x, you'll get yz. The derivative with respect to y, and the gradient, or the derivative with respect to z. Okay, and then you're going to plug in your point into this gradient, the gradient of f at my point, 2, -2, -3. That will be 6i minus 6j minus 4k. And these make up our direction numbers. So these are our direction numbers. And then I have my point. My point was 2, -2, -3. And I wanted symmetric equations, so your equations will be x minus 2 over 6, y plus 2 over -6, z plus 3 over -4. And those are my symmetric equations for the normal line.